I'm also going to record this, as I've mentioned. It's okay, I hope.
Sure.
Yeah. Okay. So I think we are, yeah, so we'll wait for a couple of minutes. Abhishek, can you check that the YouTube link is working? I'm also going to record this, as I've mentioned. It's okay. Oh, why do I hear myself twice? Oh, the YouTube link. So we'll wait for a couple of minutes. Abhishek, can you check that the YouTube link is working? YouTube link is working fine because I can hear myself. So hear myself. Yeah. So I will now log out of the YouTube link. So okay. I think I've solved that problem.
Good evening, Urvashi.
Good evening. How are you?
I'm fine, thank you. And you?
So far, we are okay.
Yeah, this news is very distressing from India.
Yes, it's not just one.
I know, it's all over.
Yeah, it's and of course we are in lockdown, right?
Yes, that I did hear.
Yeah.
Hi, Urvashi, good evening.
Good evening. Oh, that's nice to see you. It's finally you've made it to one of our. So is Ibrahim with us?
Yes.
Ibrahim, you know Ravi Rao, the first person I spoke to is from Louisiana State University. You probably already know him.
I think his place somehow is known to me, so very likely.
But the second person I spoke to is one of our, top, people from the Ministry of Electronics and Information Technology. So usually Dr. Murthy doesn't make it to our academic seminars, but maybe the lockdown helps. So Ibrahim, you have to give, I'm sure will give a fantastic talk and more. Dr. Murthy will come back again is the idea.
Yeah.
Thank you.
You're welcome.
Talking about that, I appreciate very much that you're sending these notices that I can also zoom in.
Yes, of course. Yeah, no, that is the point, to just keep the community together to the extent possible. So, so our YouTube link is also working. We are doing this first time, Ravi, trying to go live on YouTube. And
I see.
So, and it is okay. It's easy enough, but if it doesn't work, then it doesn't work. So we will start in a minute then, Ibrahim. As in, given the Indian Standard Time and the fact that many of us are in lockdown, I'm sure we are we'll join in slightly later. So 1 minute we'll give. Yeah. And so we were just hearing about how it is in Canada. And
so the vaccination was a little bit slow at the beginning. I mean, as we expected, we expected to be fast as it looked like UK or United States, but now they are catching up. And each day, I think in Ontario, they have about maybe 10,000 vaccination, which is reasonable. It's not so high, but it's reasonable.
Right.
So hopefully sometimes in September we can go to normal.
Yes. You know what? I've actually forgotten what is called normal anymore. Just being alive would be a good idea, at the moment. And for people around us.
I was making jokes with my friends that in 2020 I will not surprise if I open the window and I see an alien walking the streets. So everything happened this year.
Yes, yeah. Maybe 2021 will beat 2020 by actually making that happen. That would be a first. So 2020 was special, and this year will be even more. So anyway, so I think we will begin though, just, keeping time. And of course, we'll keep allowing people. And some are watching on YouTube already and it's working. So good. So we will formally now begin. So Ibrahim, I will begin with an introduction as always, and then I'll hand over the floor to you. Welcome everyone to today's talk in the RRI Quantum Science and Technology seminar series. We are delighted to have with us today Professor Ibrahim Karimi, from the University of Ottawa. So I'll give a short introduction, of course, I think most of you know Ibrahim very well, but then still an introduction is in order. So Ibrahim was born in Saghez in Kurdistan in Iran, that is Iran. He received his BSc degree in physics with an emphasis in mathematics from the University of Kerman in 2001, and MSc from IASBS in 2003, and PhD degree from the University of Naples in 2009. He is, of course, in Canada, and he holds the Canada Research Chair in Structured Light at the University of Ottawa. His research focuses on structured quantum waves and their applications in quantum communication, quantum simulation, quantum sensing, and material science. His contributions notably include studies pertaining to the relationship between the quantum spatial properties of photons and electrons and their internal properties. He is a member of the Royal Society of Canada, the College of New Scholars, and the Global Young Academy, a fellow of the Optical Society of America, visiting fellow of the Max Planck Institute for the Science of Light, fellow of the National Research Council Canada, University of Ottawa, Joint Center for Extreme Photonics, and adjunct professor in IISBS, Iran. He received the Ontario Ministry of Research, Innovation and Science Early Researcher Award in 2018, the University of Ottawa Early Career Researcher of the Year Award in 2019, and the Canadian Association of Physicists Herzberg Medal in 2020. Professor Karimi is also an associate editor of Optics Express since 2016 and was an associate editor of the New Journal of Physics, along with, of course, being an extremely well-published author himself. Applications of structured quantum waves, massive and massless particles in modern science and technology are the main focus research of his research team, the Structured Quantum Optics Group in University of Ottawa. Now, before giving the floor to Ibrahim, I wanted to take a few moments to reflect upon the rather special nature of today's seminar and its circumstances. The pandemic has led to many disruptions in daily life, but has also forced as well as enabled the academic world to come closer to each other, to be more close-knit than before. And this was the motivation behind starting this webinar series, as you all know. And I'm glad that we continue to listen to excellent speakers like Ibrahim and are grateful to him and others for finding time to enable such academic unity. Indeed, as we are all aware, the world in general is battling a raging pandemic, and India in particular has been very badly hit in recent times by the second wave. While we are all in the middle of a lot of pain and suffering that we are witnessing among family, friends, and people in general, and trying within our limited means to help people in need, we as scientists should not forget our vocation, and having a rational mind while trying to be helpful in mitigating the situation around is very important. So falling prey to stress is not going to help us or anyone we care about, although sometimes it is inevitable. So we should be grateful that we belong to a fraternity that takes pride in being balanced in its thoughts and action. And indeed, discussions and deliberations like this among like-minded colleagues gives us hope that this too shall pass. And we have ideas to look forward to, discoveries to make together, and intellectual capacity to contribute both to mitigate the current situation and beyond. So Ibrahim, over to you. Thanks.
Thank you very much, Basi, for your kind introduction. Thank you very much for the invitation to speak at your meeting and also in your organization. And also, please accept my sympathy. So it's really a difficult moment for all of us, but especially for India. I mean, we are following news, and we know that almost 1 million people per 3 days are affected in India. So, but human, I mean, we faced so many challenges during many years, and I'm sure that we will overcome these issues and these challenging times. So just be strong and stay safe and follow the protocols. So this is what I can say. But I'm sure that with the effort that we have from frontline people, we will resolve this issue, and soon we will come back to what we say previously, normal situation. Let's hope for that time. In any cases, life is going on, and we have to be strong. And thank you for organizing these sort of events. I mean, this is one way that we can be strong, and we can be all together and learning new things and maybe finding discoveries. I remember a while ago when I was giving a talk at the University of Bristol, Sir Michael Berry and I, we had a discussion, and he said to me, was not only Newton that came out with a lot of discoveries during the pandemic time, also Shakespeare wrote many things during the pandemic time. So many discovery happens during that time, and it's a difficult time for all of us, but let's stay together and be strong. So thank you very much for the invitation, Basi, and today, hopefully, after the presentation, we can have fun discussions and maybe follow up conversation about maybe potential avenues for collaboration between let's say University of Ottawa, Canada, and Raman Institute. So as Urvashi kindly mentioned, my research is focused on structured quantum waves, and I focus on either photons or electrons, the two elementary particles, two of those elementary particles. And sometimes also we are touching other, let's say, quanta, shaping them, understanding what's going on with internal degrees of freedom between them. So today's discussion, since we are mainly interested in photons, is about only structured photons and Z application in quantum photonics. So I will have two of those applications, which is quantum simulation and simulating complex system, and the quantum key distribution, which will be two subjects that I will cover at, let's say, 2/3 of my talk. So when I talk about light, I mean, either from the quantum perspective or from the classical perspective, we know light that is solution to Maxwell equation. Maxwell equations, they are relativistic, so we don't have any problems to do the boost and moving to different frames. When we deal with Maxwell equations, we understand that light is, or electromagnetic field is made of electric and magnetic field, which they're coupled to each other during propagation in vacuum. Let's concentrate for the time being in vacuum. And then we can talk about frequency or K vector, if you will, if you like. Then we know that electromagnetic field also is has vectorial nature. So this is the way that electric field or magnetic field is oscillating upon the propagation time in space and time. So when we talk about vectorial nature, then we are talking about polarization of light. And then we know that light also, if you look at the scalar field, then you do have also phase and also a probability distribution for, if you're talking photonic regime, in the single photon regime, you also have a distribution for light in the transverse plane or along the propagation direction. So if I want to talk in terms of quantum mechanics language or second quantization, then for linear momentum, I have a Hilbert space, which is continuous. So I can tune any K vector that I want. But however, polarization only will take two values since it's in the transverse plane. So this is a vector space that I do have it for the, let's say, a bidimensional vector space that I have it for polarization of light. For phase and intensity distribution, since most of our optics, they are cylindrically symmetric, we prefer to do the quantization in cylindrical coordinate. And then when you do this quantization, you end up with a phase, which this phase along azimuthal direction also is quantized. This is what we call it orbital angular momentum. And the eigen state is given by exponential of IL phi, in which phi is the polar azimuth polar angle. And if you look at the intensity distribution in the transverse plane, also you have a radial degrees of freedom, which also is quantized. The nature of the last two, they are discrete quantities, however unbounded. So they can, the only thing that bonds them is the numerical aperture of your lenses, your mirrors, fibers, or whatever that you do have it in the laboratory. So in general, we do have access to all of those, plus the photon number distribution, which is another degrees of freedom. In the laboratory, we can create them. We can create any of those sort of beams with technologies like spatial light modulator, DMDs, or Pockels cells, or many different techniques. So one of the techniques that was invented in Italy, and I was educated there, is using liquid crystal technologies. So what we do, we essentially coat two pieces of glasses, we keep them at the distance of 4 micron, and then point by point, we write a specific structure on the top of these. So we align the polymer, and then when you inject the liquid crystal, then you will get a specific orientation or pattern on the liquid crystal. Then when you shine the light on the top of these, then you can manipulate phase, intensity, and polarization distribution of light. And by switching the input polarization states, then you can switch the state. This is based on Pancharatnam-Berry phase, which is a category of geometric phase, essentially. So then, for example, these are a few examples that the thickness is about 4 micron. If you want to watch it, really, you can hold it with your hand. And even in 2014, I made it with my colleagues to be a dimension of 18 nanometer thickness. So you can really go to really small dimensions. And when you illuminate light on the top of these, you can get what we call it structural light, and you will see it in a few slides what I mean by structural light. But in that moment, remember that with this, we can control intensity, or let's say field distribution. You can control phase distribution, and also in some cases, you can control the polarization distribution. And by quickly switching the input polarization state, you can manipulate also the output one, which can go even to gigahertz repetition rate. So these are 2 examples that you can create in Scotia beam, or we can create Airy beams. Those people, they work in optical trapping, they know that these beams are very useful for them. Or we can create a beam which has a topological charge of 400. This was a challenge for ourselves, how big, how large in terms of OM space we can go. So essentially, this was one of the nice work by one of my PhD in my master students, which he was able to write a pattern that when you shine light on the top of these, you can get orbital momentum of 400. Lovely. So then when I talk about structural light, I mean that photon wave function, I mean, I have to be careful with the word of wave function, is a coherent superposition of frequency, polarization state, photon number, radial mode, and orbital momentum. So essentially, I have 5 different degrees of freedom. And in the photonic community, we are fighting to get access to control all of these 5 different degrees of freedom. So spatial mode, which is P and L, which is unbounded, as we discussed. Photon number, either you can go with a coherent state, or you can go with, let's say, biphoton, you can go with squeeze light, even thermal light if you wish. You can go also with polarization degrees of freedom, which you can manipulate what's going on with the polarization, or you can even go with different frequencies. You can go with a combination of coherent combination of modulo of several different frequencies. So as an example, you can see on the right side that I have a coherent superposition of L equal to 1, P equal to 3, 1, 2, 3, P equal to 3, and left-handed polarization, plus P equal to 1 and orbital momentum of -3 and right-handed polarization. So they have 2 different polarization states, but each of these 2, they have a different mode. So one of them is what we call it LG mode of 3, 1. The other one is LG mode of 2 and -3. So when you go with the coherent superposition of these, then you will get a distribution for photons, or you can get a field in the coherent way, I mean, out of a laser, which has intensity profile, which is given by this avocado color, which look like a donut shape with some pattern. But however, point by point, the polarization state of light is changing. This is what I call by structural light. So with naked eyes, you don't see anything. You see only the intensity distribution, or if you put a camera, you will see intensity distribution. But each point has a specific polarization state. It looks like, I mean, in this specific case is qubit still, if you want to watch it in quantum language. But if you have many of them, you can get a QD, photonic QD. So these are a few other examples. For example, the first one is circular polarization with OM cases. Then you will get a donut shape. Every point, the polarization is circular. The other one, what we call it vector beam, which essentially you will get a superposition of 2 left and right-handed polarization, but having opposite orbital momentum. Then what you will end up, is a pattern for polarization, which everywhere is linear, but the linear has a specific topology around in the transverse plane. Or the third one, which I just described, or the first one, which is very complicated pattern. So we call those all structured photons. Good. So before going to the quantum application, it's good to know what are the properties of the physical property of these structured photons. So we know very well that concentrating only on the polarization state, then we know that the polarization state is bidimensional. So you can map it on a Bloch sphere or Poincare sphere. And then you can have left-handed, right-handed, like spin up, spin down, exactly look like a qubit. And then when you go with the coherent superposition of these two, you will be anywhere on the sphere. If the your qubit is not pure, you have a partially mixed state, then you will be somewhere inside of the sphere. So when you go to the North Pole or South Pole, then you have left-handed and right-handed superposition. In general, we know that the polarization will be described by a polarization ellipse. So it can be an ellipse, which you have an arrow where the electric field tip is oscillating around this. So for this ellipse becomes singular in two different cases. When it becomes linear polarization, then we don't know where the polarization will oscillate, either going, let's say, in the opposite directions. We have no clue about that. So we call this a singularity, which is not associated to zero of the field. The field is there, but we don't know a property about the polarization ellipse. Mathematically, these look like S3 to be equal to 0. The Stokes parameter of the Z component or SZ will be equal to 0. Or when the polarization ellipse becomes a circular polarization, then we have no idea about major and minor axis of polarization ellipse. So ellipse becomes a circle. So in this case, the Sx and Sy, they will be equal to 0. So mathematically, we can define singularities for polarization. And when we talk about the structural light, essentially, we can have very complicated pattern of polarization singularities. For example, this is an example of a lemon topology. I don't want to talk about what is the lemon topology, but just remember that point by point, the polarization is changing. So it means that the polarization ellipse has a specific structure. And then you will see at the center is circular polarization. We call these C point. And at the periphery is somewhere in the specific radius is linear polarization. We call these L line. So, and when upon propagation of photons, or let's say electric and magnetic field light, then you will get a C point becomes a C line, and L line becomes L surface. This is what Michael Berry, Sir Michael Berry, and John Nye they quantify, and they say that all of those major polarization, all of those polarization topologies are quanta of lemon star and Mond star topologies. Good. So we can also look at the very complicated situation when you have one of those complicated polarization pattern, and look at the regime which you are not in the paraxial regime. So you can look at the tightly focused case. If you take one of those topologies, for example, the topology of star previously, and do the tight focusing, essentially what you will end up with, you will end up with a very complicated polarization pattern. Due to the tightly focusing, you don't have the field only in the X and Y plane, but also along the propagation direction, a field will appear, which the magnitude is much smaller. I mean, half of the intensity, or let's say the field at in the transverse plane. But however, what is happening, the field becomes non-paraxial. In this case, if you reconstruct the polarization along X, Y, and Z, and relative phase between them, what you end up with is that if you plot all of the polarization ellipses, they becomes from the in plane, they becomes become a three-dimensional topology, which all of those ellipses, if you follow them, they form a Mobius. And this was a puzzle for community, which with my colleague in Max Planck, Peter Benzer, Gerd Loix, and Bob Boyd, we performed the experiment, and we observed that yes, a two-dimensional, let's say, a paraxial beam, which you have a specific topology for it. When you go to non-paraxial regime, you will get a three-dimensional topologies, which this topology, it can form a Mobius. So for example, this is an example of these, which you could get a Mobius. However, you can also get more complicated pattern upon propagation. So for example, this is one case which we do have a structured photons or structured light, which which we do have a very rich topology. For example, in some places, here we have a lemon topology. In some other places here, we have a star topology. And if we let this beam to be propagating, then what you will end up with a knot. So those points of, let's say, lemon and star for the C points, they evolve in the space, and after a while they annihilate. And if you follow them, then you will see that you will get a knot for these point of singularities. So this is an example of trefoil knot, and also with my colleague Mark Dennis in the University of Bristol, we try to look for, they develop a technique that you can look for the cipher surface when the knot is embedded in, and they could qualify if whether we have a proper knot or not. And then for one of those examples, they look at the first figure 8 knot that we created, and they were able to quantify that we do have the proper topology. And very recently also, one of my master students, he tried to combine knot and Mobius, so what we call it frame knot. And from the frame knot, they were able to associate prime numbers to each braid's representation, and then they could have a protocol which is look like RSA protocol in the classical regime.
Excuse me, Ibrahim.
So, yes.
Just so you know, you're actually speaking to people also. But then, do you want to take questions during the talk, or do you want everything in the end? Because some questions have started appearing. So would you like to answer them as you go along, or how would you like to do it?
It is up to you. If you want, we can answer them right away. Can you please explain how the polarization along different directions are reconstructed experimentally? Okay, absolutely. So this goes back to, let me see if I can go back to the question. This goes back to that one. Okay. So essentially, the polarization, the reconstruction polarization technique was developed in Max Planck Institute. So what they do have, you do have the beam which is tightly focused. Then they have a substrate which they have a nanoparticle there, which is about 80 nanometer dimension. Then when the light is coming in and shining on the particle will act as a scatter. Then scatters the beam, scatters the light. In terms of, you can express them in terms of YLM, and you can collect them in forward and backward. And by having those information, you can reconstruct what is the component of X, Y, and also Z, because these look like let's say a metallic sphere, which a dipole which is oscillating there. So the technique by itself was published, I think, in 2000. If I'm not wrong, either 12 or 13 in Nature Photonics. If you send me an email, I can send you the proper reference. Okay, I think that was the only question, right?
Yes, so far.
Okay, good. So let's go to okay. So we were here. So as I say that you can have a frame knot, and this frame knot has a specific braid representation. And then these braids, they have specific twist. And we develop a protocol which is look like RSA protocol, totally classical. And when you can encode prime numbers on each braids, and we develop how people they can use this braid as a backdoor for classical communication. Of course, it's secure because this braid representation is unique, and also access to which node is encoded there, access to it will be computationally costly. So and also, as I say, that so far we just look at the polarization, how the transverse mode can be used, but also people, they can look at the way that you can control also the frequency. You can have what we call it polychromatic structure light. So in this case, 2 frequency or 3 frequencies will be joined together. I mean, you can have a coherent superposition of them in such a way that all of those frequencies, they are mode locked, but each of them, they have a specific, let's say, structure. They can be, each of them, they can be accuded, and then you can encode the information in this higher dimension. So this is an example that my students, they look into that. So if you have 2 frequencies, what you get, you will get a Lissajous pattern. You don't have a polarization ellipse anymore. You have something like a Lissajous pattern with a 3-fold symmetry. And also, if you add a 3rd frequency, and if you look at the propagation along Z on the tight focusing, you will have some sort of knot, which each point they have a specific knot information. And then even you can look at the density of those knots and how they are distributed in space. And also, just to note that also one of my good colleague, Konstantin Biliuk, also prior to us, he developed a similar technique, but for the case that is not tightly focusing regime. You can also generate them in the laboratory by going through high harmonic process when during the high harmonic process, this quanta of light will be transferred to higher harmonics, since there should be a conservation of linear momentum and also angular momentum there. And with this technique, we were able also to create a magnetic field by interacting with the material, and then we can create, let's say, about few Tesla magnetic field when this first harmonic and second harmonic are properly shaped and properly locked to each other. So also in the quantum regime, you can look at the process when you have these spatial mode, let's say LG modes, going under, let's say, spontaneous parametric down conversion, when one photon is absorbed by the crystal, a nonlinear crystal, and then you get, let's say, 2 entangled photons. So far, people, I mean, including myself, but many other people, I think first time was Anton Zeilinger team, which they look into the correlation between orbital angular momentum, degrees of freedom. So they showed to the people that if you start from a pump, which is Gaussian, then always the daughter's photons, photon pairs, always they have a conservation of total angular momentum. So if one of them has orbital momentum of 1, the other one has -1. And since we don't know which one is which, then you will get entanglement in orbital momentum degrees of freedom. And this year, since there were not much interest in P until 2012, which Enrico and myself, we find out that P also, the radial degrees of freedom is a good quanta. Then also we looked into the way that you can get the P degrees of freedom. So if you look at the case when you have a P equal to 2, then we have a conservation of parity along along the transverse direction, along radial direction. Then we can look what is happening when you create photon pairs. And we show that also in the case that when you have photon pairs, essentially there is some sort of correlation due to the parity conservation in the transverse direction. So if you look at LS and LI, which is the angular momentum of either and signal, there is a correlation there. But in each of those subspaces, also there is a correlation between PI and PS. And that was a nice way to engineer entangled state. I mean, higher dimension entangled state. And this was a tomography in dimension 16, which shows to us, yes, the state that we are looking for is really feasible, and you can create them with 2 photons. Good. And now I'm with
Ibrahim,
the quantum. Yes.
Yeah, if I may ask a question as well. Yeah, no, if I can ask a question on the previous slide. So you've done this tomography. So exactly how many measurements did you do to reconstruct the state here? So this was a 16 dimension?
In order to do the 16, you can go with a qubit case, right?
Mm-hmm.
So for each qubit, you do need 4, right?
Right.
So 4 multiplied by 4 is, I think...
6. But 4 multiplied
16.
by 4 is 16. Yes.
Yeah, let's do that. Let's do the mathematics. So essentially, you need to reconstruct the density matrix, essentially, right? So which the density matrix is 4 by 4. And then we have upper one. So that is 4 multiplied by 3 divided by 2, which is 6. Am I wrong? No, that is 6.
No, the math is, yeah. Mm-hmm.
And each of them is a complex number, so multiplied by 2, it will be 12. So I think we let me remember. I think there is a formula for that. I've forgotten.
No, I mean, my question was more not really about the exact number, but then, you know, in tomography, we actually scale in the order of d square. So the question was more, yeah, what was it like 16 square? What are we looking at here? We're looking at 4 square or what are we?
Yeah, it should be 4 multiplied by 3, essentially. 12 multiplied by 12, 122. 144, sorry. 144 as the number of the measurement.
Okay, maybe we can discuss later about how complicated that could be. Yeah, please go
absolutely ahead. Yeah, absolutely. So here is, since it's a dimension, let's say the point is that is 4, right? Is 16, which essentially is 2 power of 4. So since is a prime power, we have no problem to do what we call it mutually unbiased basis, right? So the group here is SU4, SU16, which essentially you have 15 generators. And from the 15 generators, we can build up the full tomography. Mm-hmm. The problem happens for the cases like D equal to 6,
for instance. Okay. Yes, yeah,
which is 2 multiplied by 3. In those cases, what you have to do, you have to go do over complete tomography.
Right.
Which means that you have to split it in 2, you have to split it in 3. So here is essentially you need 4 measurements. Here, what you need is something like 9 measurements, and then multiply these 2 together, you get 36 one. Okay, this is what people they do.
Right. So we have a question here. We have a comment here. SU16 has 255 generators. You probably have SO4.
Yes. Sorry. Yes, it's SU4. My apologies. You are totally right. Yeah. My apologies. Is SU4. Is not SO4.
Okay. And there's one more question, Ibrahim. If P is the radial mode index of LG beam, what conservation is followed by PS-PI correlation? Is it radial momentum?
So the point is that, look, if you look at the right, let me clean this one. And just to tell you that talking about the tomography, also remember that mutually unbiased basis, or let's say looking for the generators, Aninda, thank you very much for correcting me. Yes, you are right. Totally is SU4. If you go for cases like which is not the power of prime number, like 16, like 15, and 6 and 15. In those cases, what you can do, you can go with SIG POVM state, symmetrically information complete basis.
Right.
And those we know how to build up. I mean, we know the code for it, and we know very well that in any cases, when it's not a power of prime numbers.
You mean when the exponent is not a product of primes, right?
Yes, when it is not the case of, let's say, P equal power prime number power of n, okay, or for the case of, as I said, for the case of 2 multiplied by 3, or let's say 2 multiplied by 5, 2 multiplied by
3
6,
multiplied by 5.
3 multiplied by 5. All of those cases, they are not power of prime numbers, right? Is a product of 2 prime numbers.
Yeah, so 2 times 6, so 6, yeah, that's right. So 6, of course, you're saying 2 times 3.
Yeah, so
I mean,
then
because,
we don't know.
Yeah, so some orders, so what you're saying is that for some orders, we do not really follow the same procedure, but we could do SIC POVMs, and we could,
Exactly.
also reconstruct the state. Okay.
Yeah,
so
exactly.
I mean,
When it's prime number or power of prime numbers, we know the solution. Then we can go with mutually unbiased basis.
Right.
And when it's not the power of prime number, when it's look like the case of 2 multiplied by 3 or 2 power of 2 power times 3, then we can go with SIC POVM.
Right. And in this case, Ibrahim, so this high dimensional state that you have is, so it is an entangled state. So it's a bipartite entanglement.
Yes, it's a bipartite.
So it's a 4x4 state, is it?
Is a Q quartz, yes. 2 Q quartz.
2 Q quartz, yes. Okay. Okay. Yeah,
exactly.
Please. Yeah.
Exactly. Okay. So regarding the question that it was about, if P is the radial mode index of LG beams, what conservation is followed by PS? Okay. Look, this is an excellent question. Remember that when we go with a P, essentially, let me write it down here. So essentially, we end up with some specific pattern like this one. Oh, the intensity pattern is like this, right? This is what we have as a pump. So just before the BBO crystal, we have a field which is like this, okay? So essentially, between each ring of intensity here, here, and here, there is a pi jump. So here, if the first one is 0 phase, the other one is a pi jump, the other one is 0 phase again. So there is a sum, if you look at the phase in the radial part, then you have a uniform phase of 0, then you have a uniform phase of pi here, and then you have a uniform phase of 2 pi here, which is exactly 0 again. Then if you create photons, essentially photons should be following the field continuity. So the 2 photons together, if you look at them, you should see at the near field exactly the same field, right? But now it's not a single photon, it's biphoton system. It's a photon pair, okay? So then it means that the 2 photons, which you do have is LG, PI, LI, LG, PS, LS, the product of these 2 should follow the field continuity plus the phase matching function of the BBO crystal. So essentially multiplied by LG, P of the pump, and L of the pump star, that should follow a specific, let's say, relation in the transverse plane with the phase matching. So in physics, I mean, what do we mean by having correlation in PS and PI? The correlation will be dictated by the radial parity that you have. So how the 0 and pi jump will appear. So if one of them, for example, if one of the photons has, let's say, uniform phase, which is P equal to 0, then definitely the other one should follow exactly the same phase jump that will be 0 and pi, 0 and pi. So that is the physics here. Good. I hope that is clear. Should I move on?
Yes, please. Yeah.
Okay. Absolutely. Good. Now that we know a little bit about structured photons, now we can discuss about application, their application in quantum communication. How many minutes do I have?
You know, I think we can go for, say, half an hour, because we're taking questions as we go along. So 25 minutes, half an hour, we'll say. Yeah.
Lovely. Okay.
Yeah.
So I do want to discuss about the basic of quantum communication. So in quantum communication, I mean, we have different protocols, but let's say the QKD. In QKD, what is happening that we do communication, Alice and Bob, they do the communication. So they have a public text or cipher text, which is shared. And then we don't know even the key prior to sharing it. Then what we do, we share sequence of, let's say, state, and then finally Bob performs the measurement. I mean, of course, you need two bases, two mutually unbiased bases for BB84 standard protocol, and then Bob performs the measurement in randomly in one of those two bases and gets the information. And finally, the two people, they will share the basis that they perform the measurement, and after shifting, they have a key. They have a sort of key, which requires also the privacy amplification. However, I mean, I don't want to talk about the classical BB84 protocol, but remember that now when we go with QDIT, which essentially is n alphabet that we do have, is not only limited to 0 and 1. For example, if we go with the dimension 8, then we do have 0, 0, 0, 0, 0, 1, 0, 1, 0, and etc. until 1, 1, 1. So we have essentially 3 bits of information. So going to higher dimension will allow you to send more information per photon. And then also from the security analysis, what we get a very interesting property. So for example, this is a dimension 7 that we do have. So this is look like our 0 alphabet, 1, 2, 3, 4, 5, 6. So we have a 7 letter that we can share. And essentially, we can have also different mutually unbiased bases. So we can have Psi1 and Psi2. They just look like if you want to look at the eigenstate of eigenstate of sigma x and sigma y, so you cannot measure them simultaneously. So essentially, if you take any Psi1, any state from the Psi1 and doing the projection on Psi2, then what you will get, essentially, you will get 1 divided by 7, which is the property of mutually unbiased bases. So when you are in the wrong base, then you cannot get the information. However, what is happening if you go to higher dimension, if you go from the qubit to q quartz, what is happening if you don't have any error? If you have 0 error, you can send 1 bit or 2 bits of information. If you go to dimension of 8, then you can send 3 bits of information. If you go to dimension 16, you will get 4 bits of information per pulse, per photon, essentially, per shifted photon. However, we know that there is a key rate, essentially, which this key rate, secret key rate, also dictated by the number of errors that happens in the system. So how many errors do we have in a system? So for example, in the qubit case, we do have, if you have 0.11 error, then the positive key rate is 0. So this is what we call it is a security threshold for the error. However, if you go to dimension 4, you can increase or you can push these limits to about 0.19. If you go to dimension 8, you can go push it to almost 0.25. So going to higher dimension, having access to higher dimension is not only beneficial in terms of the secret key rates, but also is important in terms of noise tolerance. So there are more noise tolerance in terms of being sensitive to noises. So essentially, also they will provide us some sort of sensitivity. So also gives us the way that we can detect the presence of Eve much easier. So just to have a feeling how the higher dimension will be useful, we can, this is an experiment that we have done in 2018, which we look at the different protocol, for example, Chow 15, BB84, standard way, or tomographic one, BB mutually unbiased basis, or Singapore protocol, which is based on the SIGP or VM protocol. And we try to go from dimension 4, dimension 8, dimension 2, dimension 4, dimension 8, or dimension 2, dimension 4, and dimension 2, okay? And we try to look at for all of those cases. And what we were expecting, I mean, there is a error threshold for all of them. And you see that, for example, for the case of two-dimensional BB84 protocol, this is about 11% error. If you go to dimension 4, as I said, it's about almost 19%. If you go to dimension 8, that is almost about 25%. And different protocols, they have different ability. I mean, they can send more information, or they can handle more noises, and etc. And we had a setup which allows to essentially allows to change from different protocols, all of those, without human interface. So without anyone interrupting the system. So the system could pick up one of those protocols, perform the measurement, and let's say sharing the key between Alice and Bob. And we look at different scenarios, and just we want to see that if our detectors or generation techniques, detection techniques, or let's say single photon sources, which essentially was let's say SPDC. Of course, we look at the G2 function again and G4 function in such a way that there is no security problem, etc. And we find out that with the current technology that we do have, which is a avalanche photodiode detector, and going for this specific wavelength, which is 710 nanometer wavelength, which is the highest efficiency that we can get in APDs, it turned out that dimension 4 is the best dimension for us, because if you go to higher dimensions, the imperfection in detection and generation system also causes some noises that you don't get a much better key rate. The key rate is even essentially lower because you have more noises in the system. So, and then also we look at the
Ibrahim,
yes.
The previous slide. Can you please explain once more this significance of the last column? So what are you doing here? R experiment multiplied by 15. So what is this range indicating actually?
So this is the key rate when you don't have any error.
Okay, yeah,
right?
yeah.
For different protocols. This is the experimental errors that we observe in the laboratory.
Mm-hmm.
This is the shifting that you have to do.
Right. And so
right?
you have multiple.
So for example,
yeah.
So for example, in CHA 15, you have to multiply by 1 divided by 6. So 6 out of 5 times out of 6, you have to throw away the state,
Mm-hmm.
okay, the information. While for BB84, usually we go with half, right? Because it's a 2 mutually unbiased bases. But also you can go with the bias scenario, which essentially you use one of the bases to share the information, and sometimes you use other mutually unbiased bases just to get the evidence that Eve is present there or not. So this is there are other protocols that people they dictate. For tomography protocol, you go with the number of mutually unbiased bases. For example, if dimension is 2, then we have 3 mutually unbiased bases. So then 2/3 of the time you have to throw away the information. For dimension 4, you have 5 mutually unbiased bases. Only 1 out of 5 you will pick up the proper information.
Right.
And then total will be.
So Ibrahim, the point that I'm trying to understand here is that your experimental error also is kind of increasing with dimension, right?
Yeah, but this error is not due to the presence of Eve.
No, it is experimental error. I mean, because
Exactly.
So then you win some, you lose some, and so that is why you are kind of boxing that particular range and saying that here you would win and lose in the correct proportion. Because if you go higher,
Exactly.
then your error. Okay, yeah. Okay, so I get it.
Exactly.
So there's not much advantage then of going higher than that for these protocols, because your errors will then supersede whatever advantage you gained.
Exactly. And
Right.
if you can get a better detector, better source, better generation, better detection, then you may go to higher.
Right. Yeah. Okay, thanks. Yeah.
Beautiful. Okay. Then we in a few slides, I want to just show that what is the advantage of going to higher dimension. So one of the security, as we discussed, there is a security threshold. Higher dimensions also, they are sensitive to presence of Eve. So let's see that. So essentially, we know that there is no cloning theorem. I can prove it in two lines. I mean, people, they prove that in 2 lines, based on linear algebra. I don't want to go for these, but assuming that I have a quantum state. So Urbasi is sending me a quantum state of psi. And let's say the wave function is for electron, not for photon. Then I say to Urbasi, okay, I can do the cloning, which means that I can make a perfect copy of what Urbasi sends to me. So I have now 2 wave functions. So I have wave function of psi that you send it to me. Then from this wave function of psi, I have a magic machine, which I can get 2 copies of psi. Then for the first one, I can perform the measurement in X. The other one, I can perform the measurement on P. Then I can get 2 non-committing operators, the value for 2 non-committing operators with 100% certainty. This is against uncertainty principle, which we learn in quantum mechanics. So definitely then this action is forbidden by quantum mechanics. You cannot make a perfect copy. You can make copies which look like psi prime and psi second, but these 2, they will follow again the same uncertainty principle, which is limited by h bar divided by 2 or whatever that we will have. So this is the logic essentially that is behind what we call it optimal quantum cloning machine. So essentially in the optical quantum cloning machine, what is happening is that we have a quantum state, we send it to a machine, and we send it to a machine. Sorry. Okay. Yes. We send it to a machine which is optimal quantum cloning machine. Then the pure state of psi now becomes a mixed state of rho 1 or rho 2. So it means that if the vector is on the surface of Poincare sphere for the qubit case, now the direction is a proper direction, but now the point is not anymore inside on the sphere, but is a little bit inside of the sphere. And the same scenario here if you do the symmetric cloning machine. Then this can be done by Eve. So Eve can have such a sort of machine which can attack to a quantum communication system and make it 2 copies, one keep it for herself and sending the other one to Bob. So if you do this sort of attack, which what we call it optimal quantum cloning attack, in the case that we didn't have attack, which is like this is the experimental result for no attack, experiment for no attack. Then for the case, then we do have a optimal cloning machine as an attack to the system. Then you see that certainly in detecting the state in the diagonal side, now it reduces to a value which this value is dictated by optimal cloning situation. So what is happening? The presence of Eve will introduce some noises in the detection that Bob performs. So if you follow this, then for dimension 2, this is what we get. For dimension 2, that will be the amount of error that Eve will introduce. In the dimension 3, this will be the amount of error that Eve will introduce. Dimension 4, etc. Dimension 7, you will see that will be the amount of error that Eve will introduce to the system. And you will see that going to higher dimension essentially will allow you to see the presence of Eve much easier. So going to higher dimension essentially is beneficial because it reveals the presence of Eve much easier. So there is a question, I think, is the optimal cloning machine state dependent? Or okay, exactly, fantastic. So yes, there are protocols that people, they have it for optimal cloning machine, which is state dependent. However, the technique that we do have, I mean, if you want later on after the talk, I can describe it to you. It was universal. So as you see that it goes also with different mutually unbiased spaces. So we check that is independent of the state, is universal one. Good. So we try to build up a communication system, which is Alice and Bob. They perform, let's say, they share a key, and intermediate we have Eve, which Eve does some stupid, or let's say, smart attack to the system. So one of the attack which we know very well is intercept here. So Eve detect the states and then generate the states and sending back to Bob. This is the most trivial one, which we call it intercept resent. And the other one is optimal quantum cloning one. And then we check what is happening for dimension 2, dimension 3, dimension 4, and dimension 5. In the case when you have no attack, this is a pure experimental case. When we have optimal cloning attack, which is what is happening here, you will see that the action of this box, which is what we call it the transmission box or transmission channel, we can quantify what is the action, what is the process matrix of this action. Then also we can look at the intercept resent, which you can see that in the case of no cloning, essentially the action of these is look like unitary, is it look like identity. And if you go to the cloning, you will see that there will be some presence of between the, let's say, cross channels. And essentially, if you go to the intercept resent, you will see that the quantity will reduce much lower and the noises will introduce higher. So this is the way that also proves that in going to higher dimension will provide you more security. In 2017, we brought some of our equipment outside of the laboratory, and people in my team, they performed a QKD between two buildings at the University of Ottawa. So the distance between them, these two, they were about 300 meters. And I think the height was about something 20 meters, something like that, if I remember well. And they created single photon there. And also they use this, they send the classical channel in the same way, just to monitor the turbulence. And they use the 4-dimensional state for QKD. Here is more alphabet, is not only limited to 0 and 1, but also it goes to 0, 0, 0, 1, 1, 0, and 1, 1. And they try to perform QKD in higher dimensions using BB84 protocol, which is, again, 2 mutual ion bispaces. And if you look at the, let's say that you have a sensitive camera, one single photon camera, and you look at the photons that they are coming to you, in all cases, if you accumulate them, you will see a donut shape. So the information is encoded in the polarization degrees of freedom, polarization orbital and momentum degrees of freedom. This is what we discussed at the beginning. So this is the structured light essentially allows you to go to dimension 4. So then they perform in the let's say with the polarization, they perform in the 2 dimensions. This is the result of 2 dimension. And also this is the result of 2 dimension. They got about 5% error due to the turbulence, due to the imperfection in the system, which they got about 0.43 beats per shifted photon. And they moved also to dimension 4, which we had about 11% error. But still with 11% error, we were able to send more information than 2-dimensional case. So in the case of 2-dimensional, it was a 0.43 beats per shifted photon. Here we got about 0.65 beats per shifted photon. So if I want to watch it, just pay attention to this. The threshold in the 4-dimension now is increased to almost 19%. And we had a scenario which we had about 11% error, which the 2-dimensional was completely useless, but we still could get the information to be transmitted or positive key to be shared in the 4-dimensional case. Right now, we have a link of 5.4 kilometers, which we do have also a scintillometer to monitor the turbulence in real time. We can see what's going on with the turbulence, which is the main issue really in the QKD, free space QKD. We have a very fast adaptive optics, which can go to 3 kilohertz, essentially to compensate for the turbulence. And even the link is available on the Google map. You can go there, or Google Earth, and you can see also the link. And due to the pandemic, we all shut down completely now, so we cannot do any sort of experiment. And they tried back in 2019, at the end of 2019, to do some QKD. The problem with free space QKD, the problem in Canada is not only the pandemic, also because almost 6 months we cannot do any free space QKD because we have winter and the temperature is almost minus 30, minus 40 degrees and it's snowing. So then,
Ibrahim, related
yes.
to this point, how is snow different from rain?
Snow scatters. Right?
More, right? Because it is
Yeah.
kind of not liquid. Okay.
Yeah, but let me turn your question to a puzzle. Okay.
Mhm.
Assuming that you have a clear sky, okay, clear air, you do the QKD, free space QKD, and then suddenly it starts to rain. What is your guess? Will the channel will be better during the clear sky or during the rain?
Yeah, this is something I want to do and tell you, because that is indeed what we wanted to do, and then we also shut down because of the pandemic. So without the rain, we will have more dust. And so in our country, of course, I'm not sure. In some sense, we will probably have more, these aerosol particles floating around in the absence of rain. Maybe rain can clear things up. But then I don't know. Maybe you know a more scientific answer to this question.
Yeah. So in 2000, I think it was 2015 or 14 that when we did the experiment, I was very, very surprised. So we were in Erlangen essentially.
Yeah.
We started this project from Max Planck Institute with Gerd Leuk's team and Christoph Market. So when we tried to do the experiment and suddenly it started to rain and we see that, oh my God, the beam is perfectly clear.
Mm-hmm.
And it was a puzzle for us why this is happening. Because the main issue with the free space QKD is turbulence, right? What is turbulence? Right. Is the gradient of temperature, right?
And so rain moderates it.
Okay. Mm-hmm. Exactly. Mm-hmm. When you have a rain, what is happening? That the temperature of air will be uniform due to the water, and then the turbulence will be minimized.
Right. But so then what about the rain droplets? So this is a related question, and I think I was going to ask the same thing. So is the OAM degree of freedom, it is affected differently by atmospheric turbulence in comparison to polarization degree?
Yeah, so look, what I can tell you is that, based on the experience, we did not quantify this. Essentially, if we look at, first of all, if the beam will, we will discuss about that. Due to the turbulence, what is happening? You have a tip tilt in the atmospheric turbulence.
Right.
So, which means that the beam goes either left, right, or up, down.
Yeah.
The shape will not change apart from, the Freed parameter that you have it, which is due to the, let's say, the dimension of the cells for the turbulence that you do have. So this is a parameter that you can have it. And for example, if you have about, let's say, 2 centimeters, 3 centimeters, then this is the maximum regions that you can get. And then the light will be scattered from those regions.
Mm-hmm.
Let me tell you in a different way. So when there is a rain, then the beam is very stable. Mm-hmm. It doesn't move up and up down. So then those free parameters will be uniform and everything will be fine in the free space, much better than the case that you have no rain.
Right.
But however, due to the droplet, what is happening? The signal will reduce.
Right.
Will be reduced to, let's say, 50% of the time that you will get. If I send, let's say, a bright light of power of P0, then I will get P1. In the case of rain, I will get P1 divided by 2. In terms of modes, I have not seen to be significantly affected. I didn't see essentially significant changes. Even in the case that when we had the rain, I have seen that OM is more stable because OM is sensitive to the tip tilt, astigmatism, etc., not really due to the losses. So this was what we observed. I don't have any quantitative measurements to share with you, but this is what we experienced.
But then your signal dropped. So what did you actually gain? So when you say that it was, it was more stable. So do you mean that your error also dropped?
Yeah, when it's stable, the error drops.
Right. So your error dropped and your signal also dropped. So then that is where you stand. I mean, because it's not quantitative. Yeah. So we have a couple more questions. Yeah, just if you wanted to take them.
Sure.
One of them is, of course, is there an optimum D? So you were discussing about, dimension going up and things improving for various parameters which you discussed. So the question is about whether there is an optimum D, and you may have already mentioned this, but I missed it. Surely there is an overhead as you increase D. So, I mean, of course, the question is that as you keep increasing dimension, at some point you have to reach some threshold, and beyond that, it may not be useful anymore. So, what is your opinion vis-a-vis what you have discussed so far? Is how it rephrase?
Yeah, I mean, we already discussed that, right? So, you can definitely, when you have no error in your system, going to higher D is beneficial. Excellent. Okay. But the point is that when you go to higher Ds, then
errors also will increase.
Error also will increase. The experimental error, which is not only necessarily related to the dimension D, but also related to, for example, the detectors, because you have low signals. Then your detector, for example, in any cases, in 1 second, clicks 300 times.
Right.
So if you have more signal, then you can suppress these. But if you have less signal, then this error plays a role, and detection and generation as well. So this is the beneficial that you can, I mean, you can look at the fight between these two thresholds.
Right. So so you want to reach an optimum, because what you're saying is that there are practical limitations to increasing it beyond a certain point, because we won't gain from the advantage that we would theoretically have. I mean, that is what, yeah. And then there is another question, why the sifted key rate is larger for 4D? I think maybe that is something you showed. Yeah.
Yeah, also we discussed that. So essentially, let's go with, I mean, I can write it here as well. So not a big deal. So when we talk about dimension 4, essentially in the dimension 4, we have 5 mutually unbound spaces, M1, M0, M1, M2, M3, and M4. Okay. So now, Alice, I mean, if you go with the tomographic protocol, I mean, you can go with a different protocol.
Why would you have? Why would you have up to M4 for 4D? You have M0, M1, M2, M3. So you also have an M4.
No, we have D+1.
That is what. Yeah. Okay. Yeah. Sure.
So now you can go with standard BB84 protocol. If you go with the standard BB84 protocol, which is was proposed, then you can only pick up one of these, two of those two, M0 and M1, or any others, okay? Then Alice picks up between these two randomly, and Bob also performs the measurement in one of these two bases, okay, M1 and M0. And there is a random chances of 50-50, then the sifting process will be 1/2. So 50% of the time you have to throw away the information because you are in the wrong base. However, there is another protocol that we call it tomographic protocol, or mutually unbiased protocol. What does it mean? That Alice has the freedom, she has the freedom to choose any of those 5, okay? And also Bob does not project only on M0 and M1, but does also project on M0, M1, M2, M3, and M4, okay? Now, what is the chances that Bob will be in the wrong base? 1 divided by 5. 20% of the time, Bob always is in the wrong base. So this is the reason that sifting sifting process will be 20% in this case, in the case of tomographic, fully tomographic protocol, not in the case of standard BB84 protocol.
Right. So we'll take one last question before, I think then we will perhaps, allow you to finish the talk. Otherwise, some people may be also. So one question is there. So there, phase changes can happen due to turbulence. So would that affect the purity of the OAM modes?
Absolutely, absolutely. It affects. You will see in the next few slides. I do have it for free space, but I did not show it here. But I have it for interesting environments, so that you will see it in next slide.
Right. Okay.
If you allow me, I will go with that.
Please do. Please do. Yeah.
Fantastic. So then that is the scenario that we did have for free space link. However, we know that 70% of the air is water. Okay. And we know that we have a lot of sensor underwater. And water is an interesting environment because essentially you cannot have all wavelengths going through the water. I mean, there's a penetration length, which at 1550 telecom wavelength is about only 300 micrometers. So it means that after 1 millimeter, essentially you have no signal if you go with the telecom wavelength. However, we have two open windows, wavelength windows for water. One is the very long wavelength, which I don't want to talk about this. It's a regime that right now satellites they are using to do communication. And the other one is at between 400 until 550 nanometers. So these are the ranges that essentially you can send signal through a clear water. So for example, for 532, you can go to 75 meters. That's a penetration length is that. For 420, it is almost 230 meters. So we look in this scenario and we try to perform some sort of, let's say, QKD in a swimming pool, essentially. Or we decided they try to do swimming in the pool party, essentially. So here exactly is the same scenario. We have structured light, which is the setup to perform QKD, and then the single photon is sent through water, and from the other side they are detecting, and this part is the classical channel that we use for communication. And if you send not, let's say, single photon, but let's say I'm sending a bright light, and if you send a bright light, an OM beam, then you will see that OM will split out. So here you will see that the OM split out in two OM modes, and then they, upon the time, they will dance, essentially. So you have OM splitting. So this is OM of 3, which you will see that it splits out in 3 quantas, and then upon the time, you will see the change of OM state. And if you characterize the turbulence here, in the free space link, essentially we have only these two. Oh, sorry, I covered that. We have only these two, which is tip tilt. Essentially, the beam goes left, right, or up, down. And in the water environment, what we see astigmatism as well. If you look at these two, you will see the magnitude is comparable, or even sometimes higher than what we have it for the other scenarios. So this is essentially an interesting scenario that we do have, which is for a new environment. Then people also, my students, they try to do QKD in a real condition, not in a swimming pool. They went to a cottage in the Ottawa River. So they rent a cottage here, and that was a perfect view that they had. That was before pandemic. And then they tried to send a signal through the water. And what they were able to achieve, it was only 5.5 meters because they were not lucky and there were rains during that time. And when there were rains, then you will see algae, it's very different environment. It's not look like going to the ocean or going to clear sea. So they had a lot of particles, which after 5 meters, they could not see the signal. And they tried to perform the QKD in polarization degrees of freedom, the standard way, and they were able to establish a secret key. And also they tried to do OAM, and what they were able to do, they went from 2-dimensional to 3-dimensional, and still in 3-dimensional, they were able to send a secret positive key rate, which is about, let's say, 0.3. But they were not able to go to higher than dimension 3. So in the dimension 4, they had too many errors to perform a QKD protocol here.
Ibrahim,
yeah.
In this particular scenario, going to higher dimension doesn't seem that great, right? Because your error is way higher and your advantage is in the 3rd decimal place, right?
Exactly.
Okay,
exactly. Yeah. Unless you have adaptive optic system.
Right.
When you have adaptive optic system, you can compensate for the errors due to the turbulence that exists in the system, and you cannot overcome that previously. So in the last year, they were able to go to a Flume in National Research Council, Canada. And what they have done there, they had ALICE on the trail, which you can move it on the trail going down and in both directions, and control the distance between ALICE and Bob. And what they have done, they performed the standard QKD in 2-dimensional space, and also they performed that in 4-dimensional case. So this is a photo of the setup, which is exactly the same scenario. And then just to show to the people that what is happening, essentially, if you send, this is a very bright laser. And you see that Alicia has a goggle, because that's really, really bright lasers. I think it's about 100 milliwatt power of laser, just to see that the penetration length of water and a laser, different wavelength inside of the water. So she had green laser and also a blue laser together. And you can see that green is scattered, or let's say absorbed much quicker than the blue. So they performed the QKD not only using the OM, but also using the spatial mode and also using the polarization degrees of freedom. And they were able to go to almost 30 meters distance in that case, even without adaptive optics compensation. And we were affected by pandemic, but we want to really go to the ocean and installing in one of those towfish and trying to do the communication with the drone and see if whether that works, or we can send information from, let's say, 200 meters under the water to a drone which is it's moving around.
Ibrahim, what was the error rate here?
So the error rate, let me remember, essentially, I don't remember the error rate, but with the gigahertz repetition rate that we had, we were able to get about 80 kilobits per second, which is much higher than what people think.
Sure, which is the key rate, but I'm just wondering, because it's a BB84, right? So just curious. Yeah, it's fine. Yeah.
I don't remember. I have to look at the paper, essentially. I don't remember really by heart.
And this is a Qtrit, is it?
Pardon?
This is a 3-dimensional system?
It's a 4.
4, right. Okay.
4-dimensional.
Mm-hmm. That's what I originally. Okay, yeah, no problem. Please go ahead. Yeah.
And this is for theoreticians. I'm sure that there are many people interested in this case. So I strongly believe that, I mean, one day we need a communication between satellites. I mean, which requires to be in a curved space-time geometry. So then with one of my good research associates, we try to look at the wave distortion when let's say the wave is propagating in a curved space-time geometry. So essentially, we consider that Alice is sending information to Bob, and then we have a very complicated, let's say, geometry, which essentially you can have a different geodesies for the communication. And we look into distortion of on the, let's say, wave function. And essentially, we look at the case, I mean, if there is no, if it's a flat geometry, essentially, we should get a psi 0, but due to the gravity, essentially we have a distortion of psi 1, which we look into the differential equation and the complicated mathematics, and we find out that this is given by Ricci matrix of the curved space-time geometry. And we look into several different scenarios, which one of them is very interesting, that if you encode in the temporal mode, then the beam after propagation will gain an error, which the error, I mean, there is a coupling between psi 0 and psi 1, which the percentage that you have it in the psi 1, which is what we call it the crosstalk, is about 11%, which is significantly higher for us. So we believe that in some cases we have to be very careful when we do communication in the curved space-time geometry. And this is the scenario. So if you send a Gaussian beam in temporal or let's say spatial mode, then what you will get a very complicated mode on the other side. And then at the end, what you have a superposition of the two modes of this one and the other one. So this is we have a follow-up work which will be on the which we'll be putting on the archive soon, which we have looked into also the distortion due to the curved space-time geometry to the Schrödinger equation, and also let's say satellite that they are around the Earth. So with this, I will complete the presentation, and then I had a few slides for simulation, but I will conclude with this that we are always interested in fundamental studies, fundamental questions like ghost imaging, foundation of quantum mechanics, let's say topologies, and also how the quantum information will be transferred to other degrees of freedom. In the electron beam, which I did not discuss about that, we are interested to build up a quantum microscope, which what we call it extreme quantum microscope, which you can extract the information with the minimum number of measurements. And also Thomas Yenovan teams in the University of Waterloo, they are leading the satellite project in Canada. And also we are member of those committee, and we want to establish a quantum internet around the Canada. So that's the entire of the goal. I have to thank all members of my team, Alicia, Fred, Hugo, Robert, Manuel, Alessio, Felix, all of those people that they try very hard to perform most of those experiments. And of course, many collaborators, international or let's say Canada-wide collaborators, national and international collaborators, including, as I say, for most of those experiments, it was with Gerd Loix, Bob Boyd, some of them with Paul Korkum about high harmonics, and my great collaborator in NRC, Khabat Heshami, Ben Sussman, Duncan Ingwen, and many other colleagues there. I'm afraid that I will miss some of those big names. So thank you very much. I think we can, yeah.
Thanks a lot. That was a wonderful talk, and I hope you can hear some virtual claps, because that's the best we can do right now. So it was very stimulating, very nice. So we've had some questions during the chat, but then now the floor is open for more discussion. If anybody has further questions, please feel free to ask.
So, Rubachi, I have to make a space here for you somewhere.
Sure. Yeah, we can
make a space for you.
So we will see if anyone else has anything else to say. So somebody has thanked you for your cool presentation. I don't know whether you've heard that adjective before. So you have been thanked for your cool presentation.
Oh, thank you.
Yes. Yeah, which is of course something I'll agree with. So does anyone else have anything else to say? Yeah, Apurva has asked, have you used time domain multiplexing for higher dimensional encoding?
No, we are going into that direction. So right now in NRC, my colleagues, they have a fast switch, which they can pick up in the time domain. And that's really important because you can suppress the noise a lot. Yes, that's a very good question. Yeah.
Right.
So if I want to translate that will be transverse mode will give you infinite dimension, essential unbounded. Then the time domain also will give you an unbounded one. So you have infinity times infinity, then you can get more information.
Sure. I think we don't have any further questions. We've already had a lot, so it was very interactive. So I think we will. Ravi is entering again, so we'll just see if he has anything to say. So he's joined us from LSU. So we'll see if he has anything to add. Otherwise, we will, of course. So we will stop the live streaming on YouTube to begin with.